Hello my dear students. Now I am going to discuss the exercise that is continuing from the previous chapter. Now you all can remember we discussed hydrostatic pressure. Pressure exerted by liquids. And you all know the equation. Pressure is given by H rho G. H is the height of the liquid column or the depth of the liquid column above which it exerts the pressure. And rho is the density of the liquid and G is gravitational acceleration. And from all the activities that we discussed, you all know that pressure exerted by a liquid column depends on the height. Not the volume, not the shape of the container, but only the height of the liquid column. And also the density as well as gravitational acceleration. So now we will do some calculations related to that topic. Exercise. The pressure exerted at the bottom of a container due to a liquid inside it is 1500 Pascal. So there is a container. If we look at the example, there's a container and there is a liquid. At this point, the pressure is equal to 1500 Pascal. What is meant by the pressure is 1500 Pascal? What is meant by that? You all know the definition. The force exerted over a unit area is pressure. So here what is the force? It is the force due to the weight of the liquid. Weight of the liquid is the force and that force is spread over the area. So the force over a unit area will be the pressure exerted by the liquid. So here the pressure exerted at the bottom of a container due to a liquid inside it is 1500 Pascal. What is meant by the pressure is 1500 Pascal. So if you write the definition as the answer, then it will be correct. So here we can say the pressure exerted due to the force spread over the surface area. Area is 1500 Pascal. That is a force of 1500 Newton acts on a, we can say on a unit area of the surface. So force acting on a unit area is the pressure. So when there is 1500 Newton acting on an area, unit area, that will be given as 1500 Pascal. And here you all know students, the unit area, the standard unit has to be 1 meter square. So here I will write it as 1 meter square because when the force is in newtons and the area is in meter square only, you get the unit as Pascal. I am sure you would have also written a similar explanation. The question was, the pressure exerted at the bottom of a container due to a liquid inside it is 1500 Pascal. What is meant by the pressure is 1500 Pascal. So the pressure exerted due to the force spread over the surface area is 1500 Pascal. That is, a force of 1500 Newton acts on a unit area of the surface. That is 1 meter square. So with that, we will move on to the next question. Second one, find the pressure exerted by a mercury column of height 10 centimeters. Density of mercury is 13,600 kilogram meter cube. So there, if we are to calculate the pressure, what is the equation we should use? P equals H rho G. So here P is equal to H rho G. H is the height, rho is the density, and G is the gravitational acceleration. So here, what is the height of the mercury column? It is 10 centimeters. Can we use that unit? No. It has to be converted to meters. So to convert 10 centimeters to meters, we need to divide it by 100. So 10 over 100 meters, and rho is given to you 13,600 kilogram meter minus 3, and you all know the gravitational acceleration 10 meters per second square. So you all know all the values. So students, when you all are doing a calculation, you have to write the equation, you have to show the proper substitution, then you do the calculation. So here of course we can simplify this. So you will get the answer as 13,600. What is the unit? Pascal. So you all know when the height is in meters, density is in kilogram per meter cube, and gravitational acceleration is meters per second squared, the answer will be in pascals. 13,600 Pascal. So I am sure you were also able to get the correct answer. With that, I will move on to the next question. The depth of a pond is 1.5 meters. Calculate the pressure caused by the water at the bottom of the pond. So the depth of the pond is given. It is water, so they have not given the density. You all should remember the density of water. Rho is equal to 1000 kilogram meter minus 3. And gravitational acceleration 10 meters per second square. So what do? We need to write the equation pressure equals H rho G. So what is H? 1.5 meters into rho 1000 kilogram meter minus 3 into gravitational acceleration 10 meters per second square. So then if we calculate, you all can see just a direct multiplication, 15,000 Pascal. 1.5 into 1000 into 10, so it is 15,000 Pascal. The depth of the pond is given 1.5 meters. Calculate the pressure caused by the water at the bottom of the pond. So the height of the column is H, that is 1.5 meters. Density 1000 kilogram per meter cube, and gravitational acceleration 10 meters per second square. So the pressure exerted is 15,000. With that, we'll move on to the next question. The depth at a certain point in the sea is 1 kilometer. Find the pressure exerted by seawater at the bottom of the sea at that point. And here you can see density of seawater is given as 1050 kilogram per meter cube. So the density is different. You all are familiar with that, students. Because there are so many salts dissolved in seawater, density of seawater is higher than the density of pure water. So it's 1050 kilogram per meter cube. So again the same equation. Pressure equals H rho G. So what is H? 1 kilometer. Again, what do you need to do? You need to convert it to meters. So 1 into 1000 meters into rho 1050 kilogram per meter cube, and gravitational acceleration 10 meters per second square. So that's how you have to do the calculation. We write the pressure 1050. So 1000, 3 zeros. Again there is another 10. So this is the pressure. This is the answer you are going to get. Or we can even write it as 1.05 into 10 to the power of 7 Pascal. In the standard way, if you write 1.05 into 10 to the power of 7 Pascal. That is the answer there. The pressure exerted by the seawater at that particular point. So you need to substitute all the values. P equals H rho G, H 1 kilometer into 1000 meters into 1050 kilogram per meter cube into 10 meters per second. So you get the pressure as 10,500,000 Pascal, or you can rewrite it as 1.05 into 10 to the power of 7 Pascal. So that is the pressure exerted by seawater. With that, we'll move on to the next one. Question number 5. A tank with a length 5 meter, width 3 meter and depth 2 meter is filled with a liquid of density 800 kilogram meter cube. So here, since these are given as length, width and depth, it's better if we can put it in a diagrammatic form. So here we have the tank like that. Okay. So what is the length? 5 meters, width 3 meters and the depth is 2 meters. So that is going to be our H. And here length into breadth will give you the area. I'm sure you all are familiar with that. So area is going to be 5 into 3. So 15 meter square. If we look at the questions, now here also the density of the liquid 800 kilogram per meter cube. What is the pressure at the bottom of the tank due to the liquid? So here we can find the pressure. For that we only need the height. So students, the first question, what is the pressure at the bottom of the tank due to the liquid? So this is the tank, you all can see. For the pressure, we only need the height. You all know the equation, pressure is H rho G. So the first question is to calculate pressure. Pressure at the bottom of the tank. That is, we will take it as P. So P equals H rho G. We need to substitute the values. What is H? 2 meters. And rho is given to you 800 kilogram per meter cube. Gravitational acceleration, you all know, is 10 meters per second square. So if we substitute those values, H 2 meters, density 800 kilogram per meter cube and gravitational acceleration 10 meters per second square. So if we calculate the value, 2 into 8, 16 and we have 3 zeros. So it's 16,000 Pascal. 2 meters into 800 kilogram per meter cube into 10 meters per second. That is going to be 16,000 Pascal. So that is the pressure exerted by the liquid column. Then we will look at the second question. What is the force acting on the bottom of the tank due to that pressure? So this is where we relate the equation that we discussed before for pressure exerted by solids and liquids. Force exerted over a unit area. So there, that is what we need to find. What is the force acting on the bottom of the tank due to that pressure? So there. If we write the second one, force acting on the bottom of the tank equals F. So pressure is equal to what? F over A. And if you rearrange, P into A will be equal to force. So we have calculated the pressure 16,000 Pascal. 16,000 Pascal into what is the area, students? You all can remember we calculated it as 15 meters squared. Why? 5 is the length and 3 is the width. So 15 meters squared. You can do the calculation before or you can do the calculation here. Either way is fine. So here it's going to be 15 meters squared. That's going to be equal to force. So you all know Pascal is Newton meter minus 2. So meter minus 2 and meter squared cancels off. You get the answer in Newtons. 16,000 into 15 meters squared. So that is going to be 16 into 15 if I multiply 8, 4, 2. So that will be equal to 240,000 newtons. That is the force. 240,000 newton. Is that okay, students? So in the previous one, we calculated the pressure. Pressure was equal to 16,000 Pascal. So then to find the force, you all know pressure is force over area. Then we rearrange the equation. Pressure into area will give you the force acting on the bottom surface. So there we find the force by multiplying 16,000 Pascal into 15 meter square. That will be equal to 240,000 newtons. So here I will write it again. Force acting on the bottom surface is equal to 240,000 newtons. So that is what we were supposed to calculate. So I am sure, students, with these calculations, now you have a good understanding about pressure exerted by liquids. The things you have to remember, pressure is equal to H rho G and that is equal to force over area. We have got understood the derivation also. We discussed how we derive this P equals H rho G from this particular equation. And then you have to look at the units. The height has to be height or depth has to be in meters, density in kilogram per meter cube, and also gravitational acceleration is 10 meters per second square. Then you need to write the equation, substitute the values and do the calculations. I am sure you all can understand that. So with that, students, we are done with the topic hydrostatic pressure and also transmission of pressure through liquids. So then I am going to move on to the next topic where we discuss the pressure exerted by gases. Pressure due to gases. So we have already discussed how pressure is exerted by solids. You all can remember, students, just to recall what we have learnt before. Now if it is a solid cube like that, due to the area and the weight, because the weight is acting downwards, that is the force, and there is the cross-sectional area. We have pressure equals force over area. Force acting on a unit area is pressure. From that we got the unit Newton meter minus 2, but that is equal to the standard unit of pressure Pascal. Similarly, when we looked at the liquids, when you have a container with a liquid, if this is the liquid, this has a density rho and that is the height of the liquid. Irrespective of the volume of the liquid or the shape of the container, the pressure exerted by the liquid is given by H rho G. So this has to be again in meters and rho kilogram meter minus 3 and gravitational acceleration meters per second square. So that will be equal to Pascal. So these are the two equations that we have already discussed. So this is due to the weight. Here also this is due to the weight of the liquid. And in addition to that, you all can remember, students, the pressure can be transmitted through the liquid. Why? Liquids cannot be compressed. So if you exert a force onto the liquid, that can be transmitted. Based on that only, we discussed the principle of hydraulic hoist or hydraulic press. Under that, the hydraulic hoist, hydraulic brakes and the hydraulic jack. All those act or they function based on the transmission of pressure through liquids. So similar to these two, the solid and the liquid, gases also will exert a pressure. Let's try to understand how that happens. Now if we have a closed container, for gases we need to have a closed container. There will be particles, gas particles. So this gas particle also has a weight. So obviously the weight of the gas particles will be acting downwards on the surface, bottom surface of the container. So if there is a weight, you all know, students, there will be a pressure exerted. Weight is the force exerted over a unit area. So that is equal to the force. Because of that, force exerted over a unit area will be the pressure. That is one way in which gases exert pressure. Because of their weight, the weight acts downwards on the bottom surface of the container, and that leads to a pressure, like in solids and liquids. In addition to that, now we can try to compress the gas. You all know gases are compressible. What is compressibility? By applying a force, you can decrease the volume of the gas. So that is compressibility. Now let's say we apply a force from here, we apply a force and we try to compress this gas. Now the gas particles will try to oppose that compression. Because of that, they will try to expand. And when they try to expand, they will exert a pressure not only on this surface, but all the surfaces of the container, because they will try to expand in all different directions. So when you exert a force, the gas particles try to expand in all directions. Because of that, they will exert a pressure. So that is the second way in which gases exert pressure. So when compressed gases try to expand. Then they exert a pressure on all the surfaces of the container. Is it clear to you all, students? So solids, liquids, gases, all are matter. They all have a mass. Because of that, they all have a weight. Because the weight acts downwards, there is a force exerted on the bottom surface of the container. And that gives rise to the pressure. Force over unit area. That is common to all. But gases, when you apply a force and you try to compress them, they try to expand. Due to this expansion, they can exert a force in all directions. That force leads to the pressure. So that is what we are going to discuss now. So if I go back to the introduction. Like solids and liquids, gases also exert pressure. There are two ways in which a pressure can be produced by a gas. And the first way, this is the first method. One is the pressure caused by the weight of a column of gas. That is what I explained to you all before. Weight of a column of a gas. Like the pressure caused by a column of liquid. The atmospheric pressure is produced this way. The air pressure, there is air around us, that's the atmosphere. Atmospheric pressure is caused in this manner. That is due to the weight of the air column. Now you have the Earth's surface, atmosphere is above that. So the air exerts a pressure on the Earth's surface. So that's the atmospheric pressure. Then the second method. The other way that a gas can give rise to a pressure is when a compressed gas attempts to expand. That is important. So when a compressed gas attempts to expand. That is what I explained in the second method. That is where the second way in which gases exert pressure. Is that clear to you all, students? So with that understanding, we will look at the way gases exert pressure. So to understand how gases exert pressure when they are compressed. When they try to expand, they exert a pressure. That is what we will try to understand now. So activity demonstrate that a compressed gas causes a pressure. So to demonstrate that, these are the required materials. First, we need a U-tube. You all know what a U-tube is, a glass tube in the shape of a U-shaped glass tube. So here of course it's after filling water, it has been shown, but it is the U-tube that you need. Then we need a balloon. So this balloon can be inflated and can be tied with a thread. So to tie it, we need thread and also we need colored water. It can be any color. That is not a problem. Why do we need a colored water? Then only you can see the change clearly. You can use normal water, but the visibility is less. You can't see the change in water levels very clearly. But when you use colored water, it's more visible. It's more clear. So that is why we use colored water. So we use a U-tube, a balloon, thread and colored water. This is what we are going to do for the activity. Now first I will explain it with the diagram, then we will look at the steps. You take the U-tube and we will label the two arms as X and Y. It can be labeled anyway, A, B or X, Y, anything is fine. So here it has been labeled as X and Y. Then you fill water to a certain level. When you pour water through one arm, you will see the water will fill in the U-tube and once you stop filling it, you can see the two levels are going to be equal. Why is that? You all know the reason. Pressure at the same level of a liquid is the same. So here you can see in both the arms, the atmosphere is exerting a pressure. Now there is air outside its atmosphere and the air can enter into the U-tube as well. So throughout up to this point, it is the atmospheric pressure. Atmosphere exerting pressure. So that's the pressure at this point and this point. And those two are equal. Why? If you really consider the depth or the height of the liquid column, it's the same. So that also leads to pressure of equal value. You all know that. Then what we do is, we take the balloon, we inflate the balloon and we tie the thread to the mouth of the balloon, but it should be tied in a manner that it is easy to remove the thread. So once it is tied, we fix the balloon to arm X. Still you can see the water levels are the same. Then what we do is, we remove the thread and observe what is happening. So here, when you inflate the balloon, what happens? You all know normally the normal balloon has a small volume, but the rubber is flexible, expandable, so elastic actually. So because of that, when you blow the balloon or when you inflate the balloon, you can see the volume increasing. But there, what we do is we try to contain a large volume of gas within a small space. So there we compress the air. So inside the balloon there is compressed air. Compressed air. Once we connect the balloon with air in it, and when you remove the thread, what does air try to do? Always when it is compressed, it tries to expand. So when it expands, it will try to exert a pressure. That is what we are going to observe. So these are the steps in the method. Pour water into a U-tube as shown in the figure. That is this first one. Then the water levels in the two arms X and Y would become equal. That is diagram A. Tie the opening of an air-filled balloon with a piece of thread, making sure that it can be easily untied. Next, connect it to the arm X of the U-tube as shown in the figure and tie it with another piece of thread. So we need to tie it to the arm so that the balloon will not come off the tube, because when air is trying to expand, if it is not tied, it can come off. Now slowly undo the knot on the balloon and remove it. Then only you need to observe what happens. So I am sure this is a very simple activity, students. You all can understand the activity. Let us go to the lab and do the activity now. Okay, students. So now we will try to understand how gases exert pressure. Like solids and liquids, gases exert pressure due to their weight. Always weight acts downward, so because of that they exert a pressure at the bottom surface of the container. That is one method. Then you all know about compressibility of gases. Gases can be compressed easily. How do we do that? By applying a force, we try to reduce the volume of the gas. So then gases get compressed. The same way, now I have inflated this balloon. When we say inflate a balloon, we try to accommodate a large volume of gas within the small volume here. So that means we have compressed air in this, or compressed the gas inside the balloon. Then here I have this glass U-tube connected to the stand, and inside that I have colored water. Again, you all know, students, the reason for using colored water, it is more clearly visible. Here we will be observing how the levels of the water inside the two arms of the U-tube will change. That is what you need to observe. So it's more easy to observe when we have colored water. Now as you can see, in both the arms, we have water, colored water, and you can see the levels of water inside the arms. In both the arms, it's the same. So, also you know that pressure at the same level of liquids is the same. So, that means at this surface and at this surface, the pressures are equal. So, that is when the balloon is not connected. So, I am going to fix the balloon here. Now, observe clearly, students, the levels of water in the two arms are still the same. So, then what do we do? I will be loosening this knot around the mouth of the balloon so that the compressed air can escape in. So, now observe what will happen. Right. So, now I have taken off the twine there. Now can you see the levels? This is lower, this is higher. There is a difference there. What is the reason? Initially, air was compressed inside the balloon. Now when I remove the twine, the air comes out and the compressed air exerts a pressure onto this water surface. Due to that pressure, The water was pushed down here and the pressure was transmitted and the level rises up in the other arm. So from that, we can understand that air exerts a pressure or gases exert a pressure. And that pressure will be equal to the height difference. Now here you can see, students, if we take it, this is a rough idea I am giving you all, otherwise you can measure also. So from this level to this level, there is a height difference of about this much. So the pressure exerted by that liquid height is the difference between the pressures in both the arms. Now even if I push and exert some more pressure, if I try to release some air by pressing the balloon, you can see the water level further changes. Now when I release it normally, you all can see a small difference. When more force is applied, you can see how the pressure changes. So from that change, you all can understand that the compressed gas or compressed air exerts a pressure. And that pushes the liquid column down here, which rises up onto the other side. The difference in height of the liquid columns, from using that height, we can calculate the pressure exerted by the air inside the balloon. That is the pressure exerted by the air inside the balloon. You all know the equation H rho G. So the height is going to be the difference in these two levels. I am sure you all can understand that, students. Okay, students. So you all saw what happens when we remove the thread from the balloon. You were able to see that the water level in arm X goes down and it increases in arm Y. That is the observation. So first I'll write down the observation. When the thread is removed, water level changes as shown in the figure. So this is also given in your book, figure C. So like this, the water level will change. The water level decreases in X and it increases in Y. Now we'll try to understand what happens there. If I mark these 2 points. Now here you can see, students. Right. So initially the water levels were the same. So then I told you all it is the atmospheric pressure that is acting on that surface of water, that you all know. So here also, if you look at this point, at this point, atmospheric pressure. Pressure or the pressure exerted by the air around us, that is acting at that point. Then you can see from here to here there is the water column. So that has a height h. Then what is that pressure? Pressure exerted by that liquid column above this particular point. So there is pressure exerted by the water column. So then what is the next point you all know? Pressure at equal levels or same levels of a liquid is the same. So pressure at this point and this point have to be same. So what can you say now? At this point, there is the pressure exerted by this water column H and the atmospheric pressure. So earlier at both the surfaces, there was only the atmospheric pressure. Now the pressure has increased. The same pressure is acting at this point. So how did that pressure increase? It increased because of the air here. Initially inside the balloon, the air was compressed. When we remove the knot, when you remove the mouth of the balloon. The air that has been compressed here tries to expand. So when it expands, it exerts an additional pressure on this surface. That is why the water level is pushed down and the pressure has been transmitted, and on this side the water level has been pushed up. That is again to displace the water, but still when you try to understand the pressure at this point is now greater. The reason is the air that was compressed has exerted an additional pressure. That is what you need to understand. So from that, what can we conclude? We can conclude and say the gas that was or air that was compressed within the balloon exerts an additional pressure on the surface of water in arm X. That is why the water level changes. So if we write it down, air was compressed inside the tied balloon. When the thread is removed, the air expands and exerts an additional pressure on the surface of water in arm X. Therefore, the water is pushed down in arm X. Because the pressure at the same level of a liquid is the same, the pressure on the surface of water in arm X is equal to the pressure exerted by the water column in arm Y above the point plus the atmospheric pressure. Atmospheric pressure. This is more than the pressure when the water levels were equal. So from this, we can conclude and say that the gas exert a pressure when it tries to expand. So that is the conclusion of this activity. Let's go back and look at the observation and conclusion again. So this is what we observe, students. The water level goes down in X and it increases in Y. So as I told you before, when both the arms were exposed to the atmosphere, the pressure exerted by the atmospheric air is the pressure acting on the surfaces. That was in the previous diagram. You all can remember that. So here both were atmospheric pressure, that you can remember. So once we open the or remove the thread and allow the air to expand, you were able to see the change. So thereafter, at these 2 points, the pressure is equal, but this point, the pressure is equal to the pressure exerted by the water column H and the atmospheric pressure. So it is an addition of both the pressures. So that is equal to pressure at this point. So you can understand that is greater than the previous instance. So that means the air that was compressed inside the balloon tried to expand, and because of that it exerted an additional pressure there. That is the conclusion of the activity. So here, this is the explanation. Air was compressed inside the tight balloon. When the thread is removed, the air expands and exerts an additional pressure on the surface of water in arm X. Therefore, the water is pushed down in arm X. So there, because the pressure at the same level of a liquid is the same, the pressure on the surface of the water in arm X is equal to the pressure exerted by the water column in arm Y above that point. So that is the pressure exerted by the water column plus the atmospheric pressure. So it is a sum of the two pressures. So this value or this is more than the pressure when the water levels were equal. So from this we can conclude and say that the gas exerts a pressure when it tries to expand, or gases exert a pressure when they try to expand. I am sure you all can understand that concept. So with that, students, I will move on to the next slide. Since the pressure at all points on the same level of a liquid is the same, the liquid levels that are equal before connecting the balloon show that the pressures above the water levels of the two arms are equal. That you all can understand. By filling a balloon with air, we try to restrict a large amount of air inside a limited volume. So that is what I told you all. By filling a balloon with air, we try to restrict a large volume of air inside a small volume. That is, we compress the air, compressing the air. When we connect the balloon filled with compressed air to arm X, the water levels are no longer the same. So here what we mean is, after removing the thread, we allow the air to expand. The higher water level in arm Y than the water level in arm X shows that the pressure in arm X at the liquid surface is higher than the pressure in arm Y at the liquid surface. That is what I explained to you all in the previous slide. The reason for the higher pressure in arm X is the additional pressure exerted on the liquid by the compressed air in the balloon. So here it is the additional pressure. There is an additional pressure exerted on the liquid by the compressed air in the balloon. So when we try to compress air and it tries to expand, because of that it exerts an additional pressure. That is what we need to understand here. So like the solids and the liquids, especially like the liquids, gases also exert a pressure due to their height. That is on the bottom surface of the container. That is one way in which gases exert pressure. And this is the second way. When they are compressed, they try to expand. So when they try to expand, they exert an additional pressure. I am sure it is clear to you all now. So with that, I'll move on to the next slide. So then we'll try to understand atmospheric pressure. When I explain the activity also, students, I mentioned this atmospheric pressure. And before that, we discussed, so atmospheric pressure is an example of the pressure exerted by air similar to a liquid column. We looked at two methods by which air exerts pressure. In that, atmospheric pressure comes under the first type. So let's look at it. Atmospheric pressure. Earth's atmosphere extends to hundreds of kilometers above the surface of the Earth. So you all know that if we look at the surface of the Earth, now we have the Earth's surface. Above that, there is the atmosphere. So here you can see, students, this is the atmosphere. And you all know atmosphere has many layers, and there are layers of air, and this air exerts a pressure. So that is a pressure exerted by the atmosphere. So that is what we call as atmospheric pressure. Similar to the pressure produced at any point inside a container filled with water by the water above that point, a pressure exists at any point in the atmosphere due to the weight of the air above that point. So let's say if we take this point of the atmosphere, there is air and there is weight of air. Weight of air. And this weight causes the pressure. That is what we call as atmospheric pressure. This pressure is known as the atmospheric pressure. So you all can understand that the Earth is there. Around the Earth there is the atmosphere with different layers, and this air in the atmosphere has a weight, and weight is the force. So force exerted over a unit area becomes the atmospheric pressure, similar to a liquid column. The atmospheric pressure was measured for the first time by the Italian scientist Torricelli. Torricelli is an Italian scientist who first measured the atmospheric pressure. And for that, he used an instrument that is shown in the diagram. The instrument he used for that purpose is shown in the figure given below. And this particular diagram or this particular instrument is called the mercury barometer. The reason is we use mercury in this. Mercury. That is Hg. So how do we make this? We take a small container with mercury, say a small beaker. Tiny beaker is enough. It doesn't have to be very huge. So we need to take a certain amount of mercury there. Then we need to have a long glass tube, and one end of the glass tube has to be sealed. And then you need to fill mercury into that glass tube. You have to fill it up to the mouth. It can be a very thin tube. It doesn't need to be a capillary tube, not a capillary tube, but it can be a thin tube. So you take the thin tube with one end sealed, fill mercury into that, invert the tube, and without letting the mercury to flow out, you have to keep it into this container with mercury. So this is mercury, this is also mercury. This is also mercury Hg. So then once you set it like that, if you clamp it. If you hold it in place and if you clamp this tube, you will see initially the mercury was filled up to the top level. It was completely filled with mercury. But once you fix it, you can see the mercury column coming down a little bit. And there will be a certain height for this mercury column. So if we look at the parts, this is the mercury barometer. So there is mercury in the container, mercury inside the glass tube. One end of the glass tube is sealed. And then once you invert the tube, mercury column comes down. Now let's mark these points, this height, this particular height as H. That is the height of the mercury column. Okay. So above that, now we fill the tube completely with mercury. After inverting it, the mercury column comes down. Because of that, there is nothing inside here. So that is going to be vacuum. Vacuum, you have the mercury column and mercury inside. Now this is how the pressure is exerted. Now I mark this as H. So you all know pressure is equal to H rho G. So this particular mercury column will exert a pressure H rho G. And that pressure will act at that point. At the same time, now these areas around the tube, there is pressure being exerted by the atmosphere on the surface of the mercury. You all know that. Even in the previous activity, I told you all there is atmospheric pressure acting on the surface of water. The same way, there is atmospheric pressure acting on the surface of mercury there. Then, what can you see? Now, these levels and this level are the same. So, we know at any point at the same level of a liquid, the pressure is the same. So, the pressure acting at these points and at this point is equal. But we have already seen that the pressure exerted by this mercury column, that is H rho G, that is also at this point. So, that pressure exerted by this mercury column will be equal to the pressure acting on the surface. That is the pressure exerted by the atmosphere. So, because of that, pressure exerted by the atmosphere, on the surface of mercury in the container that will be equal to the pressure exerted by the mercury column in the glass tube. So that is how Torricelli measured the atmospheric pressure. So he measured the height of the mercury column and he calculated the pressure using the height, and that was equal to the pressure exerted by the atmosphere. Why? Because the pressure at the same point in any direction of a liquid is the same. So that is why the pressure can be measured using this mercury barometer. Is that clear to you all? And there are few things, students, that you need to remember. In this mercury barometer, this has to be vacuum. There can be no water or no air. If there was something like that, the mercury column will come down. Why? Because the substance or matter that is inside that space will also exert a pressure. So then you won't get a correct reading. It has to be vacuum. You have to remember that. And also, you can look at this diagram. You can see the glass tube is somewhat up. It is not touching the bottom surface of the container. Even if you push this tube down until it touches the surface, still the height of the mercury column from this point to this point, what I have marked as H, will remain the same at a certain environment. Why? Because the pressure exerted by a liquid column depends on the height. So, if this height H does not change, that means the pressure doesn't change. So, it doesn't matter whether the glass tube is up, it shouldn't be above the mercury surface, it has to be inside the mercury surface, but it is not a must for the tube to touch the surface. And we have to clamp it so that it is held in place. Even if we use a broader tube, then also the height will be the same. You all know that. The pressure of a liquid column does not depend on the volume or the shape. So, you can use any shape of glass tube, you can use any size, still the height of the mercury column will be the same. So, that is an important thing that you have to remember, students. So, here this part has to be vacuum, and this is the height that gives the pressure of the atmosphere. And normally, if we use this mercury barometer at mean sea level, 0 level, mean sea level, the pressure is equal to 76 centimeters of mercury or 760 millimeters of mercury. So, to get that height, we will need to use a tube that is about 1 meter long. If the height of the column increases, the mercury column increases, pressure is higher. If the height of the mercury column is less than 76, that means the pressure is lower than the normal atmospheric pressure. Those are the things that you need to remember, students. So, this is the mercury barometer used by Torricelli. In this, the atmospheric pressure at this point is equal to the pressure at this point. That is equal to the pressure exerted by the mercury column. So, it is H rho G. In that, density of mercury is the same always. So, we will be using mercury all the time. Gravitational acceleration is the same. So, because of that, we can use the height to denote pressure. That is what I said as 76 centimeter mercury. We will look at all these explanations again in the next few slides. Okay. So, here this is the explanation. This instrument can be made of a glass tube about 1 meter long. So, I told you all this before, students. The glass tube has to be about 1 meter long. Why? Now, we said the height of the mercury column is 76 centimeters. So, the tube has to be more than that with one closed end. So, this instrument can be made of a glass tube about 1 meter long with one closed end. The tube is filled with mercury turned upside down while making sure that no air enters the tube, and then immersed in a container of mercury as shown in the figure. So, here also the figure is given, but you have to remember that no air enters the tube. So, I told you all, students, there should be no air, no moisture, nothing should be there. It should be vacuum, just empty space. So, then when the tube is mounted in upright position as shown in figure, it would be possible to see that the mercury column in the tube drops by several centimeters, leaving an empty space above the mercury column. So, when we say mounted in upright position, it has to be straight, and also, as I told you all, it has to be below the mercury surface inside the container, but it need not touch the bottom surface of the container. It can be in between, there's no problem. And when we say mounted, we have to clamp it also. We have to have a stand and we have to clamp it to the stand so that it is upright and exactly straight. then it will be easy for us to measure the height of the mercury column. The height of the mercury column left inside the tube is about 76 centimeters. This is an important value that you have to remember, students. You all have to remember the height of the mercury column. 76 centimeters. Especially at mean sea level, the atmospheric pressure is given by the height of the mercury column. I explained that to you all before also. So now, here you can see the same diagram is given to you. Torricelli understood that all the mercury in the tube does not flow down to the container because the atmospheric pressure keeps pushing on the mercury surface exposed to the outside. So that this is what is meant here. Now when you invert the tube, the mercury will try to flow down. But the atmosphere is exerting a pressure, that is a push down to this surface. So because of that, the pressure will be transmitted through the mercury liquid and that will push this column up. So although the mercury column tries to come down, there is a push given to that mercury column due to the atmospheric pressure acting on this surface. So that is why this particular column is maintained. It doesn't flow down completely to the container. So that is how we get the height as well. So you can remember, students, this is the height and that is 76 centimeters. Is that clear to you? So then, however, the atmospheric pressure is sufficient to balance the pressure of a mercury column with height of 76 centimeters. Therefore, the height of the mercury column is a measure of the atmospheric pressure. That is very important. Height of the mercury column is the measure of the atmospheric pressure. Because no air can enter the space above the mercury column, that space must be a vacuum. So there has to be a vacuum there and the height of the mercury column will be able to balance the atmospheric pressure. So therefore, the height of the mercury column is proportional to the atmospheric pressure. Is that clear to you all? So this is the instrument used by Torricelli, mercury barometer. With that, if I move on to the next slide, we know, so here you can see, we know that any 2 points at the same level of a liquid have the same pressure. So that also I explained to you all. Accordingly, since the pressure on the mercury surface outside the tube is equal to the atmospheric pressure, a point inside the tube at the same level should also have the atmospheric pressure. By considering the height of the mercury column, the pressure at the point inside the tube can be calculated using the formula P equals H rho G. Therefore, the atmospheric pressure must be equal to H rho G. Is that clear to you all? I explained everything before, so this is the explanation given again to you. However, as a convenient unit for measuring pressure, the height of the mercury column is often used. If the experiment is done at the sea level, the height of the mercury column would be 76 centimeters. So because of that, now you can remember P is equal to H rho G. So P is proportional to H, while rho and G are constants. Now if you take a particular liquid, rho density is constant and anyway G is always a constant. So because of that, to denote pressure, we say equal to centimeter mercury. Like if it is 76, we denote it as 76 centimeter mercury. You show what the liquid is and we say the height. So that is also equal to 760 millimeter mercury. You have to say the height and we have to say it is the mercury column. And there should be a space between centimeter and mercury or millimeter and mercury. So at mean sea level, the height of the mercury column in mercury barometer will be equal to 76 centimeters or 760 millimeters. Then, if we look at the explanation, if the tube is immersed further into the container with the mercury, the height of the mercury column would remain at 76 centimeters. The space above the column would be reduced in height. I will explain those. If we incline the tube, even though the physical length of the mercury would increase, the vertical height of the mercury column would remain at 76 centimeters. I will explain both those changes to you. So here. Now let's say we will have, I'll draw 3 containers. The same container with the same amount of mercury. And then we have the tube like that. Then we can have the tube inclined like that. So we have the closed tube in all instances. These are the instances that were explained to us. So this is the normal instance. Here you can see up to here, this is going to be 76 centimeters. Here you can see the tube is slightly up. The height from this surface of the mercury in the container to this point is going to be 76 centimeters. Now we have pushed the tube down. Still what will happen is, it will be like this. The same height, 76 centimeters, but this height has decreased. It has decreased. Why? We push the tube down. So this space will decrease. It's vacuum, so there's no problem. But this height from the surface of the mercury in the container up to this point is going to be the same. Why? Because the pressure exerted by a liquid column, here the mercury column, depends on the height. So we are looking at the pressure at this point, here also at this point. So only this height is important and that will not change. Whether you have the tube slightly up or below, the height is the same. Is that clear to you all? That was the first explanation. Here you all can see, if the tube is immersed further into the container with mercury, the height of the mercury column would remain at 76 centimeters. The space above the column would be reduced in height. Is that clear? Then what do? If we incline the tube, even though the physical length of the mercury would increase, the vertical height of the mercury column would remain at 76 centimeters. So we have the inclined tube there. Then what will happen? This will be like that. So if you look at the vertical height from this point to this point, if you measure that length, this length will increase. This length of the mercury column. Now here length of the mercury column and the height of the mercury column, it's the same because it is vertical. But here, because it is inclined, the length will increase. But if you measure the height from this point up to this point, this is going to be 76 centimeters. That height will not change. You all can understand that. When the tube is inclined, the length of the mercury column will increase, but the height from this point to this point will not change. You all can understand this as well. Now, we discussed an activity before where we use different containers of different shapes. From that activity, you all were able to understand, students, the pressure exerted by a liquid column depends only on the height of the liquid column, the vertical height of the liquid column. It does not depend on the shape, it does not depend on the mass. So here, from this to this, the shape has changed. That is why the length of the mercury column has increased, but the vertical height does not change. That is what you need to remember. So here we have here students, we have the tube which is somewhat above from the surface. The height of the mercury column is 76. Even when you push it down, immerse it further down until it touches the surface of the container, still this height of the mercury column remains the same. Only thing is this height, the height of the vacuum will decrease. Then when we incline the tube, the length of the mercury column will increase, but the height of the mercury column will remain the same. So that means in all three instances, the pressure, atmospheric pressure is going to be 76 centimeter mercury. Is that clear to you? Or it is equal to 760 millimeter mercury. And this is the unit. Because it's convenient to measure the height, we conveniently express the atmospheric pressure in centimeter mercury. Although the standard unit of pressure is in pascals, we express it in centimeter mercury. Is that clear to you? So with that, students, what I will do is I will do a calculation and we will try to find the equivalent of this pressure in Pascal. So here, what are the things you all know? Pressure is equal to H rho G. We know the H as 76, but it is in centimeters, so we have to divide it by 100 to get it in meters. Then the density of mercury is 13,600 kilogram per meter cube. And the gravitational acceleration is 10 meters per second square. So here, if we simplify the values, it will be equal to 76 into 1,360. If we do the calculation, 1,360 into 76. 21. So then 8. So then we have 0, 0, 42, 7 into 6, 42, 4. So 21 plus 4, 25, and 7 plus 2, 9. When we add them together, 3, 10. So that is going to be the pressure. 103, 360 Pascal. So this will be equal to 1.0336 into 10 to the power of 5 Pascal. So as a rounded value, we can consider the atmospheric pressure that is equivalent to 76 centimeter mercury as equal to 1 into 10 to the power of 5 Pascal. or the exact value is 1.0336 into 10 to the power of 5 Pascal. Is that okay, students? So that is equal to the pressure. Pressure exerted by the atmosphere. Normally we measure it in centimeter mercury. 76 centimeter mercury. I told you all have to remember this value. So that is equal to this amount of Pascal. 1.0336 into 10 to the power of 5 Pascal. I am sure you all can understand that. So that is the mercury barometer. Now just think, student. Mercury is somewhat poisonous. It's harmful. So but why do we use mercury? Can't we use water? We can. But the problem is, we will be doing a similar calculation later. When we use water, now you can see density of mercury is 13,600. With that, we need to have a mercury column of 76 centimeters. But if you use water, the density of water is 1000. That is about very much less than mercury. So because of that, we will need to use a very, very tall column of water. That is not practical. Even this, it is difficult to carry it around. You can't use it at any position. It can be used only at a certain position. If you use water, the column will be very, very tall. So it is not going to be practical. That is why we use mercury as the liquid in mercury barometer. So I will write that as well. So we can say mercury is used instead of water. Because of its density. We need a tube of about 1 meter height for mercury. But if we use water, we will need a very long tube. That is not practical. What is the reason? Density of mercury is 13,600 kilogram meter minus 3, whereas density of water is 1000. So density is 13.6 times more denser than water. So if you use water column, you will need to have a column that is 13.6 times more than the mercury column. Roughly you will have to use a tube of 11 meters in height. Now even with 1 meter, you all know how the mercury barometer will be. If we are to use about 11 meters of glass tube, that is not practical. So that is why they use mercury, or that is why Torricelli used mercury in his barometer. Is that clear to you? So as I told you, students, even mercury, one thing, it's harmful, it's difficult to handle. Even with the 1 meter tube, it is somewhat difficult to use it. But that was the initial barometer, the mercury barometer used by Torricelli to measure atmospheric pressure. But later, scientists came up with another type of barometer where we don't use any liquids, and that is called the aneroid barometer. So Before I go into the structure of aneroid barometer, we will move on to the next slide. While the atmospheric pressure at the sea level is 76 centimeter mercury. So here you can see atmospheric pressure is 76 centimeter mercury. As we move up from the sea level, the height of the air column decreases and the atmospheric pressure decreases. That you all know. When we go to higher altitudes, the pressure drops and the atmospheric pressure decreases. So as you go up, you all know that students, at higher altitudes the pressure is less. For example, the atmospheric pressure at the top of Everest is about 25 centimeter mercury. So you can understand that Mount Everest is the highest peak. So there you can see the pressure is 25 centimeters, almost 1/3 of the atmospheric pressure at mean sea level. At mean sea level, it's 76 centimeter mercury. But as you go up, it drops to 25 centimeter mercury. Very less pressure. In addition, the atmospheric pressure can change according to the weather. So it will depend on the weather as well. The instrument constructed using mercury in order to measure the atmospheric pressure is known as the mercury barometer. That is what we discussed so far. So then I told you all students, to avoid all the issues related to all the drawbacks or disadvantages related to mercury barometer, the scientists came up with the aneroid barometer. So that is what we are going to look at next. So here the diagram of an aneroid barometer is given to you. First I'll explain the diagram. So here you can see students, this is a scale and there is an indicator. You can see that indicator is connected by a chain to a lever structure like this, and there is a metal structure there. Inside that you can see to this part there is like a rod connected, and here we have a container. It's like a metallic container. It's closed, and inside that there is cavity, and inside the cavity there is vacuum. There is no air. Air is taken out. So that means there is nothing inside the cavity. So because of that, when you have a metallic cavity, you all know metals are flexible, they are ductile and malleable, and when atmosphere exerts a pressure, due to that pressure, the shape of this cavity will change. So here you can look at all these small arrows, pressure due to the atmosphere. So when the pressure is less, the compression or the push on the surface of the metal will be less. If the pressure increases, the push will be more. So based on the atmospheric pressure, the shape of this cavity will change. Now here you can see that is connected to this rod, and that again is connected to the indicator. So when this changes, the indicator will move and it will point to the pressure in the scale. So that is how we measure the atmospheric pressure here. This particular aneroid barometer functions in a mechanical manner. So here we don't have any liquids, and it is an aneroid barometer. So there. In addition, there are barometers that do not contain a liquid. They are known as aneroid barometers. So, aneroid barometers. Figure shows an aneroid barometer without a liquid. It has a cavity bounded by thin metallic walls. So, cavity bounded by thin metallic walls in which air has been evacuated. So, I told you all it is a vacuum. When the pressure outside barometer varies, the shape of the walls of the cavity also varies. That's important. The shape of the walls of the cavity also varies. An indicator attached to the cavity walls rotates with the variations of the shape of the walls. The pressure can be read out from an attached scale. So this is what I explained to you. So I am sure students, with that you can understand the aneroid barometer. So we discussed in detail the mercury barometer that was used by Torricelli to measure atmospheric pressure. And now we have looked at the aneroid barometer. So with that, I have completed atmospheric pressure, but in the next slide, we will look at some applications of atmospheric pressure. Applications of the atmospheric pressure in daily life. So the first application is drinking with the use of straw. I will explain the diagram first. So here you all can see, students, there is a glass of water, let's say, and the straw is put in. When we suck from the straw, what do? We draw the air out of the straw. Initially there is air inside the straw. When we suck, we pull the air out. We draw the air out. So what happens? There will be space here, or there will be decrease in pressure inside the straw. At the same time, the atmospheric pressure. Here you can see the atmospheric pressure will be acting on the surface of water or the liquid. So the atmospheric pressure is always pushing the liquid down. When we draw the air through the straw, due to this push, liquid will be pushed down and the liquid will enter into the straw. That will be drawn into the mouth. That is how the atmospheric pressure helps us to drink using a straw. Is that clear to you all? When we suck the air out through the straw, due to the push from the atmospheric pressure, the liquid travels through the straw. When we drink using a straw, we suck the air inside the straw and that air enters the mouth, reducing the pressure inside the straw. That's important. Reducing the pressure inside the straw. The pressure at the liquid surface outside the straw is at the atmospheric pressure, while the pressure inside the straw is less than the atmospheric pressure. Why? We have drawn the air out. Therefore, the atmospheric pressure pushes the liquid in the glass into the tube and the liquid moves up through the straw. So, this is a very simple thing. I am sure you all can understand that. Atmospheric pressure helps in drinking with the use of a straw. With that, I'll move on to the next application. The second one, removing the water in a tank using the siphon method. So here I will explain the method first. So siphon method, you have a tank here, tank A. We need to remove the water from tank A into tank B or container B. Now from fish tanks, if you want to clean the fish tank, before doing that you need to take out the fish and also you need to take the water out. So to do that, we can use this method. So here the important things are, you have to have the first container at a higher level, whereas the second container has to be at a lower level. Then what we do is, there is water in this container B or will be empty. Then we use a rubber tube like that, a plastic tube or a rubber tube. The tube has to be filled with water, and while closing this end of the tube, you have to bring the tube below this level. Here you can see this has to come below this point. That's very important. Now this end of the tube has to be below this point. Why? Now you all know at the same point of a liquid, the pressure is the same. So pressure at this point is same as the pressure at this point. Only when it is below that, the pressure of this liquid will push the water down. So that is why the container A, the first container, has to be at a higher level. Second container has to be at a lower level. Then only the water or the liquid will flow out. Otherwise, the atmospheric pressure will act on the outer surface and water will not be drawn out. So here of course atmospheric pressure is going to push down like that. That's going to give a push here. There is water. There is a level difference. So because of that there is an additional pressure inside the tube. So with the help of the push from the atmosphere, water will be pushed into the tube and it will flow through the tube into the second container. That method is what we call as siphon method. If we look at the discussion, removing the water in a tank using the siphon method, figure illustrates the use of the siphon method to draw water from the tank A situated at a higher level to the tank B. That's very important. Situated at a lower level. Initially, the tube has to be filled with water and one end pressed with a finger so that water does not flow out. And then the tube should be lowered down below the level of A. That's very important. Tube should be lowered down below the level of A. That's important. As shown in the diagram. Thereafter, when the finger is removed, water starts to flow to tank B from tank A. That is the observation. I have explained how that happens also. So then you can see the pressure at the end of the tube A is equal to the sum of the pressures due to the water column in A above the end of the tube and the atmospheric pressure. So that's what I told you. There is the atmospheric pressure there is a pressure due to the water column. And here at the same levels, the pressures are the same. Since the end of the tube in B is exposed to the atmosphere, the pressure there is equal to the atmospheric pressure. So I told you all, here there is the pressure, that is the pressure exerted by the atmosphere. So if the tubes are at the same level, if there is atmospheric pressure on either side, there will be no pressure difference, water will not flow out. But here, this is the atmospheric pressure. But here it is the atmospheric pressure plus the pressure of the water in the column. So because of that, you can, if we read, since the end of the tube in B is exposed to the atmospheric pressure, the pressure there is equal to the atmospheric pressure. Therefore, the higher pressure in tank A pushes the water to the other end of the tube at tank B, which has a lower pressure. That is how the siphon method works. I am sure you all can understand that, students. So this siphon method is used in different instances. One example is drawing water out from the fish tanks. So that is a siphon method. Okay, students. So now we will try to understand how we use the siphon method. You all know atmospheric pressure helps us in different ways. So one of the ways is the siphon method. Now we'll consider this as a tank full of water. Normally you all know we have fish tanks at home. So if you want to remove water from the fish tank, that is from this tank, if I want to transfer the water into this trough. Let's consider both are tanks. So from tank A into tank B if we want to transfer water. Now look at this tank. Now there's water inside it. At the surface of the water, what is the pressure? It's the atmospheric air that is acting on the surface, or it's above the surface, it is the atmospheric air. So that air exerts the pressure, that is the atmospheric pressure. So at the surface there is atmospheric pressure. Then if you take this water, this liquid column, there is a column, so that also exerts a pressure. And you all know the pressure at the surface is less compared to the pressure at the bottom. So what we will be doing is we will be using a tube, a rubber tube to transfer water, and here we will consider the sum of both the pressures. So here what I will have to do first is I will need to fill this rubber tube. Now there is water filled in the tube. What I will have to do is I will have to bring one end to the second tank, and from this end, it has to go to the bottom, right to the bottom of this tank. Then only, as I explained to you all before, there will be a difference in pressure. At this end, it's only the atmospheric pressure. When I release my thumb, it will be exposed to the atmosphere. So, there is only atmospheric pressure acting on this end. Whereas, when I dip this into the bottom of the tank, there is pressure from the atmosphere. In addition to that, there is pressure from the water inside this tank. So, there is a pressure difference. That pressure difference pushes the water from this end to this end so that we can transfer the water. So, now this is right at the bottom, and if I take my hands off, you can see the water coming out. Can you all understand this method now? There is pressure exerted by this column plus the atmospheric pressure. But here it's only the atmospheric pressure. So there is an additional pressure in this tank that pushes the water through the rubber tube. So that is the method that is known as siphon method. So using this method, we can transfer the water from one tank into another tank. And here another thing that you need to observe. Here students, this tank is slightly above the other tank. So here another thing, to facilitate the pressure difference, we have this tank above the second tank. So there also it's easy to maintain the pressure difference. So that is the siphon method. So I am sure you all can understand this method. This is an application of atmospheric pressure. With that, I will move on to the next example. Action of the rubber sucker. So first I'll explain the diagram, then we will read the explanation. So here students, you all can see it is a surface. Now normally this has to be a smooth surface. I will tell you all why. Normally we stick the rubber sucker onto a glass or a tile that is clean and smooth. Then only it will stick to the surface. So what we do is, when we try to press the rubber sucker, now you all know this is rubber, so it's flexible. Then what will happen is, when we push it, when you press it onto the surface, the air that is in here will mostly escape out. And once the sucker is pressed onto the surface, there will be very less air. At the same time, if you look at the outside of the rubber sucker, there is the atmosphere. So this atmosphere will exert the atmospheric pressure. That is what is shown by these arrows. So the pressure outside is very much high compared to the pressure inside. Why? Because there is only a small amount of air. So due to this pressure difference, pressure from outside is greater. It will push the rubber sucker onto the surface and it will hold it in place. And thereafter, when you hang a heavy weight also, the rubber sucker still will be attached to the surface. So there, the atmospheric pressure helps us to press the rubber sucker onto the surface and to hold it in place. That is how atmospheric pressure functions here. So you all can remember students, if the surface is not clean or if it is not even, if it is a rough surface, then what will happen? Even when you press the rubber sucker onto the surface, due to the unevenness, air can enter inside. So there, the difference in pressure between inside and outside will not be enough to keep the rubber sucker intact. So that is why the surface has to be smooth. So when a rubber sucker is pressed onto a glass surface as shown in figure, most of the air between the two surfaces is removed, leaving only a little air in between the sucker and the glass surface. That is what I explained there. Only a small amount of air. Then, Since the pressure inside the rubber sucker is less than the atmospheric pressure outside, the sucker is held pressed to the surface by the atmospheric pressure. The rubber sucker would function properly only if there is no airflow between the edge of the sucker and the glass surface. So that is what I said. It has to be a smooth surface. It has to be a clean surface. So there should be no airflow between the edge of the sucker and the glass surface. So here you all can understand, students, the outside pressure, that is the atmospheric pressure, is greater than the pressure inside the rubber sucker due to a small amount of air. So that is how the rubber sucker is held on to the surface. Is that clear to you all? Okay, students. So another application of atmospheric pressure is the use of rubber suckers. You know why we use that? To hang different weights, different objects at home. It can be in your vehicle, or it can be in the kitchen, or in the storage cupboard. We can use these rubber suckers. So I'm sure you would have seen a rubber sucker. We have this surface that will be used to attach the rubber sucker onto the surface. Say the wall or a tile or even a glass is the surface to which we are going to attach the rubber sucker. And on this side, you all know there is a hook, so we can hang a weight or an object using this hook. So how does this rubber sucker function? Now you can see on this surface there is atmospheric air. So around it there is atmospheric air. So the pressure exerted by the atmospheric air acts on this surface as well as this surface. But when we press it to a surface, I'll explain it now and then I will demonstrate it. Now let's say if this is a glass surface, when I press it onto this surface, the air that is here will escape out. So because of that, if we just keep it this way, it won't stick. If we really press it, the air from inside the surface escapes out, but the air from the outside exerts a pressure onto the rubber sucker. Because of that, the rubber sucker sticks to the surface. Then you can hang a weight. So this is the way the rubber sucker sticks to the surface, gets attached to the surface. Now I have another rubber sucker because this is easier for me to attach it to a surface and to hang this weight. It's easier for me to use this one. So I'm going to demonstrate how we really use it at home. So what I will do is, I will attach the rubber sucker to this surface. So here, once it is attached to the surface, it will not come out. So as I told you, the air inside will escape out. The pressure given by the atmosphere around it will keep the rubber sucker attached to the surface. So then this is a weight. So you all can see, students, this is a wooden block. This has a certain weight. Now if I hang it, now this is of course a slightly modified one so that we can easily hang the weight on the rubber sucker. So here you can see the weight can be hung like that. So this is an application of atmospheric pressure. So I will remove the weight. Now if you want to remove the rubber sucker, if you want to remove it back, if you just pull it, it won't come. Why? As I told you all, the air, the atmosphere is exerting a pressure that doesn't allow us to pull it out. So if I just take it off from the side, you can see it easily comes off. And for the rubber sucker to function properly, we need to have a smooth surface here, and this side also, it should not be damaged. So if we can make the air from this surface to go out, when we stick it to the surface, we can use it easily. So with that explanation, students, I am sure you all can understand the function of rubber sucker as an application of atmospheric pressure. So with that, students, I will move on to the next slide where we have an exercise. So this is an example where we do a calculation. The atmospheric pressure at sea level is 76 centimeter mercury. Taking the density of mercury as 13,600 kilogram per meter cube. Acceleration due to gravity as 10 meters per second square. I have done this calculation before to you all also, students. Find the atmospheric pressure in pascals. So we need to find the atmospheric pressure. Atmospheric pressure, I'll write that as P. So what is P? P is equal to H rho G. Now if we substitute the values, H is 76, but we need to divide it by 100. Why? In order to make it to meters. Then density is given to you as 13,600 kilogram per meter cube. And gravitational acceleration 10 meters per second square. If we do the calculation, if I simplify this, so 76 into 1360. 1360 into 76, 0, 36, 6, 18 into 3, 21, and 6 into 1, 6 plus 2, 8. 0, 0, 42, 2, 4, 21, 25, so 2, 7 plus 2, 9. When you add them together, we get the value this. So we did the same calculation. We got the same value before also. 103,360 and the unit is pascals. We simplified this. You can remember 1.0336 into 10 to the power of 5 Pascal. So that is the atmospheric pressure in pascals. That is the answer to the first question. Then the second one. Find the height of a water column that can be balanced by the atmospheric pressure. Density of water is 1000 kilogram per meter cube. I explained this to you all, students. Because the density of water is less, you will need a taller water column. Now we are going to calculate that height. So what do we do here? Again, to find the height of the water column, we use the same equation, pressure equals H rho G, but we already know the pressure. That is 103360 Pascal. That is equal to, we don't know the height of the water column, but we know the density 1000 kilogram per meter cube and gravitational acceleration 10 meters per second square. So to find the height, 103360 divided by 1000 into 10. I have rearranged the equation. This is equal to H. So when we simplify that, it will be 10.336. That is going to be H. 10.336. So you will need a height of about 11 meters. So this is going to be height. Height of water column. Water column equals 10.336 meters. So it's almost like 11 meters. So 10.336 meters. So now you all can understand that, students. So because the density of mercury is very much high, the length of the water column that is needed to exert the same pressure is very much more. So because density of mercury is high, the pressure exerted by a shorter column is enough to balance the atmospheric pressure. But if you use water, the density of water is less, So you need a taller water column, or the height has to be more, and that should be equal to 10.336 meters. So you need a glass tube of at least 10.5 or 11 meters length. So that is very difficult to handle. That's what I explained to you all before. So now I am sure you all can understand what pressure is. Pressure exerted by solids, pressure exerted by liquids, transmission of pressure in liquids, and now we have discussed atmospheric pressure and the instruments used to measure atmospheric pressure, mercury barometer and the aneroid barometer. Thereafter, I discussed the application of atmospheric pressure, and we have done this calculation as well. So with that, students, I will end this chapter, and in the next chapter, we will be discussing a new topic, flotation.